transformer secondary requires 125 amps overcurrent protection. The transformer's secondary is rated at 15 kilovolt-amperes. At 120 volts, this equates to 125 amps. According to the National Electrical Code, the overcurrent protection device must be rated at not more than 125% of the transformer's full load current. To calculate this, we multiply 125 amps by 1.25, which equals 156.25 amps. Therefore, a 125 amp overcurrent protection device is the minimum required to protect the transformer secondary. Now let's delve deeper into the reasons behind this requirement and the relevant sections of the NEC that govern it. The primary purpose of overcurrent protection is to safeguard the transformer and the connected circuits from damage caused by excessive current flow. This can occur due to various factors, including short circuits, overloads, and ground faults. Without proper overcurrent protection, these conditions can lead to overheating, insulation breakdown, and potentially even fires. The NEC provides specific guidelines for overcurrent protection of transformers to ensure safety and prevent equipment damage. These guidelines take into account the transformer's voltage, current rating, impedance, and other relevant factors. Now let's consider the specific scenario described: a 15 kilovolt-ampere, 480 to 120 volt single-phase transformer in an industrial installation. The secondary leads are less than 25 feet long, and both primary leads are protected. The secondary leads, using number 2 American wire gauge wire, go to power distribution block, which then fans out with 8 number 14 wires, each with its own breaker. The power distribution block and all breakers are located in the same enclosure. The question is whether the transformer secondary needs a 125 amp overcurrent protection device. As established earlier, the answer is yes, due to the NEC requirements. The NEC mandates that transformers be protected on both the primary and secondary sides. This is typically achieved using fuses or circuit breakers. The size of the overcurrent protection device is determined by the transformer's full load current rating. The full load current can be calculated using the following formula for a single-phase transformer. The kilovolt-ampere rating is divided by the voltage, which gives the current. For the primary, it would be 15,000 divided by 480, which gives 31.25 amps, whereas the secondary is 15,000 divided by 120, which gives 125 amps. Let's break down the relevant NEC sections that apply to this situation. NEC section 450.3 addresses the overcurrent protection of transformers. This section provides specific rules for selecting the appropriate overcurrent protection device based on the transformer's voltage and current ratings. For transformers rated over 600 volts, the primary overcurrent protection device must be rated at not more than 125% of the transformer's rated primary current. For transformers rated 600 volts or less, the primary overcurrent protection device must be rated at not more than 250% of the transformer's rated primary current. These percentages are specified to allow for the inrush current that occurs when a transformer is energized. Inrush current is a temporary surge of current that can be several times higher than the transformer's normal operating current. If the overcurrent protection device is sized too tightly, it may trip during inrush, causing nuisance tripping. The secondary overcurrent protection requirements are generally more stringent than the primary requirements. The NEC requires that the secondary overcurrent protection device be rated at not more than 125% of the transformer's rated secondary current, unless certain conditions are met. One such condition is when the transformer is equipped with coordinated thermal overload protection. In this case, the secondary overcurrent protection device may be sized up to 250% of the transformer's rated secondary current. However, this exception is not applicable in this particular scenario, as there is no mention of coordinated thermal overload protection. Therefore, the secondary overcurrent protection device must be rated at not more than 125% of the transformer's rated secondary current, which is 125 amps times 1.25, equaling 156.25 amps. In this case, a 125 amp overcurrent protection device is the maximum size allowed. Let's discuss the implications of using a 125 amp overcurrent protection device in the secondary side of the transformer. This overcurrent protection device will protect the transformer from overloads and short circuits in the secondary side. It will also protect the downstream wiring and equipment from damage. The number 2 American wire gauge conductors connecting the transformer secondary to the power distribution block must be rated to carry at least 125 amps. According to NEC Table 310.16, number 2 American wire gauge copper conductors with a 75 degrees Celsius insulation rating have an ampacity of 115 amps. However, the ampacity of the conductors must be adjusted if they are installed in an environment with an ambient temperature above 30 degrees Celsius, or if there are more than 3 current-carrying conductors in a raceway or cable. In this case, it is important to ensure that the number 2 American wire gauge conductors are properly sized and aerated to carry the 125 amp load. The 8 number 14 American wire gauge conductors that fan out from the power distribution block are each protected by their own breaker. The size of these breakers must be appropriate for the ampacity of the number 14 American wire gauge conductors. According to NEC Table 310.16, number 14 American wire gauge copper conductors with a 75 degrees Celsius insulation rating have an ampacity of 15 amps. Therefore, the breakers protecting the number 14 American wire gauge conductors should be rated at 15 amps or less. Now let's look closer at the power distribution block. The power distribution block serves as a convenient way to distribute power from the transformer secondary to multiple branch circuits. The power distribution block must be rated for the voltage and current of the circuit it is serving. It must also be properly installed and grounded. The enclosure housing the power distribution block and breakers must be properly sized and ventilated to prevent overheating. The enclosure must also be properly grounded to provide a path for fault current. In summary, the transformer secondary requires a 125 amp overcurrent protection device to comply with NEC requirements. The overcurrent protection device must be properly sized and installed to protect the transformer, wiring, and equipment from damage. The number 2 American wire gauge conductors connecting the transformer secondary to the power distribution block must be rated to carry at least 125 amps. The 8 number 14 American wire gauge conductors that fan out from the power distribution block must be protected by breakers rated at 15 amps or less. The power distribution block and enclosure must be properly sized, installed, and grounded. By following these guidelines, you can ensure the safe and reliable operation of the transformer and the connected circuits. It is also important to consult with a qualified electrician or electrical engineer to ensure that the electrical installation complies with all applicable codes and standards. In addition to the NEC requirements, there may be local codes or regulations that also apply. It is important to be aware of and comply with all applicable codes and regulations. Failure to comply with these codes and regulations can result in fines, penalties, and even legal action. Furthermore, it is important to regularly inspect and maintain the electrical installation to ensure that it is in good working order. This includes inspecting the transformer, wiring, overcurrent protection devices, and other components for signs of damage or wear. Any damaged or worn components should be replaced immediately. Regular maintenance can help to prevent electrical problems and ensure the safe and reliable operation of the electrical system. Finally, it is important to remember that electricity can be dangerous. Always take precautions when working with electricity. Turn off the power before working on any electrical equipment. Use insulated tools and wear appropriate personal protective equipment. If you are not comfortable working with electricity, consult with a qualified electrician. Here are some additional points to consider. Firstly, the type of overcurrent protection device used, whether a fuse or a circuit breaker, should be selected based on the specific application and the characteristics of the electrical system. Fuses are generally less expensive than circuit breakers, but they must be replaced after they trip. Circuit breakers can be reset after they trip, but they may not be as fast acting as fuses. Secondly, the interrupting rating of the overcurrent protection device must be sufficient to handle the available fault current at the point of installation. The interrupting rating is the maximum amount of current that the overcurrent protection device can safely interrupt without being damaged. If the available fault current exceeds the interrupting rating of the overcurrent protection device, the device may fail to interrupt the fault, which can result in equipment damage or personal injury. Thirdly, the coordination of overcurrent protection devices is important to ensure that the overcurrent protection devices closest to the fault will trip first, while the overcurrent protection devices further upstream will remain closed. This helps to isolate the fault and prevent unnecessary outages. Coordination can be achieved by selecting overcurrent protection devices with different time current characteristics. Fourthly, the grounding of the electrical system is essential for safety. A properly grounded electrical system provides a low impedance path for fault current to flow back to the source, which helps to trip the overcurrent protection devices and clear the fault. Grounding also helps to reduce the risk of electric shock. Fifthly, the labeling of electrical equipment is important for identification and safety. All electrical equipment should be properly labeled with its voltage, current rating, and other relevant information. This helps to ensure that the equipment is used properly and that it is not overloaded. Sixthly, the training of personnel is essential for safe electrical work. All personnel who work on electrical equipment should be properly trained in the safe work practices and procedures. This includes training on how to identify electrical hazards, how to use personal protective equipment, and how to perform electrical work safely. Seventhly, the documentation of electrical systems is important for maintenance and troubleshooting. All electrical systems should be properly documented with wiring diagrams, equipment specifications, and other relevant information. This helps to facilitate maintenance and troubleshooting and can save time and money. Eighthly, the periodic inspection and testing of electrical systems is important to ensure that they are in good working order. Electrical systems should be inspected and tested periodically to identify any potential problems. This includes testing the overcurrent protection devices, the grounding system, and other components. Ninthly, the use of arc flash protection is important to protect personnel from arc flash hazards. Arc flash is a dangerous electrical explosion that can occur when there is a fault in an electrical system. Arc flash can cause severe burns, blindness, and even death. Arc flash protection includes the use of personal protective equipment such as arc-rated clothing and the implementation of safe work practices. Tenthly, the awareness of electrical safety is important for everyone. Everyone should be aware of the electrical hazards in their environment and should take precautions to avoid them. This includes avoiding contact with energized electrical equipment, using caution when working near power lines, and reporting any electrical hazards to the appropriate authorities. These additional points highlight the importance of a comprehensive approach to electrical safety. By following these guidelines, you can help to ensure the safe and reliable operation of electrical systems and protect personnel from electrical hazards. Remember to consult with qualified professionals and adhere to all applicable codes and standards.